All right, let's talk about singular value decomposition. Definition of singular value decomposition in a matrix. G admits the factorization, and G is equal to U sigma V subscript H, and U is a complex L by L unitary output directions, and then sigma is diagonal with non-negative singular values, and V is unitary input directions. Singular value decomposition separates directions, rotations from gain scaling. So we have already seen that. And then we talked about the description and what this means. It means that U rotates the result into output direction, or let's just start from top. Rotates V rotates input directions, and sigma stretches or shrinks the along orthogonal directions, and then U rotates the results into output directions. Or essentially V, how you push the system and how much it responds to the system, sigma how it responds to the system, how it responds, and U how it shows up at sensors. We have already seen that, so let's go back here, and then also let me define this. So start with this one. The SVD separates directions from gain scaling. So we have now for MIMO we have both directions or rotations, and then we also have gain or scaling. Then the singular value satisfies sigma I j is the root square of lambda I GHG. The matrix GHG measures how input energy is mapped into output energy, its eigenvalues, therefore determine amplification levels. Let me explain this carefully. GHG acts purely in input space. It tells us how input energy maps to output energy. But the matrix, so the matrix GHG measures how input energy is mapped into output energy, its eigenvalues, therefore determine amplification level. This is why singular values, not eigenvalues of G, measure gain. So as you see here, we have GHG and then lambda I, and then this GHG maps how it describes how input energy is mapped into output energy. Let's go back to here. So geometric interpretation of our equations. A couple of slides back, we saw G is equal to U sigma V superscript G H, and then V superscript H rotates input coordinates, and sigma stretches or shrinks along orthogonal directions, and U rotates the results into output direction. This makes sense because we need to somehow rotate input to align them with output, and then we need to measure how it shrinks or stretches. So we have either this rotation and then amplification or reduction in the input energy. And this makes sense because then again we rotate input space, in other words, and then stretch along principal axes, and then rotate into sensor coordinates, because then sensor coordinates measure what we feel. So in mechanical analogy, rotate actuator combinations and then excite principal modes and observed rotated sensor outputs. So because at the end of the day we measure sensor field, and this also shows us how we can go back from what sensors feel to what actual inputs are. So So let me add one more thing. So you're essentially choosing combinations of actuators that excite clean modes, or the modes, your desired modes. For a real 2 by 2 matrix, the singular value can be written as, as an example, let's take a look at U, and then we have G or theta 1, and then we have sigma, and then we have R theta 2. In 2D is everything is rotations plus a stretching, either stretch or shrink, or we have this rotation, no mystery, no abstraction. It's completely clear what we have in 2D. Let's also define the principal input and principal output directions. Let Vi be the r's column of V and Ui the r's column of U. Then GVI is sigma I Ui. If the input is applied along direction Vi, the output appears purely along direction Ui with gain sigma I. This is a clean experiment, meaning that if you excite exactly Vi, if you could hypothetically excite exactly Vi, the system responds exactly along Ui. If the input is applied along direction Vi, the output appears purely along direction Ui with gain sigma I. So this is the cleanest input-output behavior. No coupling remains. And then we have this sigma. Let's talk about sigma I, the amplification again, sigma ij. Since norm 2 Vi is equal to norm 2 Ui, and both equal to 1, then we have sigma G equal to GVI, the output, over the input. Its singular value is the gain associated with the principal direction. Singular values are not abstract. They are literally gains. So singular values, gains. Although there is a there is a correspondence between the gain and the singular values. Singular values are not abstract values. In engineering sense, and each singular value is the gain associated with the principal direction, with a principal direction. Maximum and minimum gains bar sigma j is equal to sigma 1g, and then max d gd0 is gd2 norm over d2 norm. And this, we have already defined these parameters: sigma max, maximum singular value, and minimum maximum gain and minimum gain. Maximum gain is gd2 norm. G was the matrix of complex elements, and then gd2 norm over d2 norm, and then we have sigma underscore g, and then that shows the minimum, the worst case scenario, and the nicest best case gains. So among all input directions, one produces the largest response and another produces the smallest non-zero response. So it's smallest by smallest non-zero response. Therefore, for all admissible inputs D underline sigma G, any output we're going to have is going to be between the minimum and the maximum. There's nothing special extra here. We're just saying that the output is between the minimum possible and the maximum possible outputs, so maximum possible gains. These bounds essentially underpin performance limits, robustness analysis, and multivariable controller design. So these bounds, that's what they show. And now, why SVD again? Singular values, just to recap, singular values quantified through input-output amplification. Input and output directions are orthogonal and physically meaningful, and the SVD applies equally to square and non-square systems. So again, just to recap, eigenvalues show internal behavior, but singular values show external behavior. Conclusion is that the SVD is the fundamental tool for analyzing gain and directionality in MIMO systems. If you remember one tool from this chapter or this this topic is, remember the SVD, what it does. Now, just give me a second. Alright, so I'm gonna stop here, and then next time I'm gonna talk about this example. Thank you.